Hello guys, this is Prime Concept. Now I want to analyze some new concepts in an electrostatic field or electrostatics. Now we have electric potential energy U and electric potential V. These two concepts are usually confusing to students because you see potential and they tend not to really understand the difference between them. But then you need to understand first that electric potential energy is given denoted by the symbol U, while electric potential is denoted by the symbol V. And we're going to explain further to differentiate between both of them. And let's say we have a charge somewhere, we have a source charge somewhere in space. Now, you already understand from our earlier videos that when you place a charge, that charge will create a field around it, right? So this is a source charge. Now, say I place another charge, a test charge Q0, somewhere at a point A from this. Let's say this distance is A, which I'm going to call RA. Now, and I want to move this charge Q0, this test charge, I want to move it closer. Let's say this is a positive charge, this is a positive charge, and I want to move this closer. You would observe that because these two forces, these two charges are positive, there's going to be an electrostatic repulsion between them. This charge will pull this charge away. So there's going to be an electrostatic force pulling this charge away. Now, if you try to move this charge, let's say from point A to a new point, say point B, what it means is that you're going to do a walk against the electrostatic force, or you're going to do a walk against this electric field, right? Now, and the force you are going to apply in pulling this from point A to point B is going to be equal but opposite to the electrostatic force, right? Now, what is the electrostatic force of repulsion pulling this charge? The electrostatic force is F equals KQ Q0 by R squared. That is the electrostatic force. Of course, this distance is your R, right? Now, if you want to pull this from this point to point B, you will do a walk, and that walk done is what we know as change in potential energy. So we'll be starting from change in potential energy before we now talk about potential energy. So what is change in potential energy? Change in electric potential energy. It is the work done in an electric field in moving a positive test charge from a point A to another point B in the field, in the electric field. It is the work done in moving a positive test charge from a point A to a point B in an electric field. So that is what we call change in potential energy, which is exactly the same as work done between those two forces. Now, you should know that the force you would apply in doing this work, our applied force, is going to be equal but opposite in direction to the electrostatic force. Now, if I consider doing work within a small distance, moving that charge through a small distance AB, right? Then that work done is going to be given by this. The integral through that distance from point A to point B times our applied force times the distance, the small distance, the R through which you are moving, right? And what is our applied force? Our applied force is the negative of the electrostatic force. So if I bring that into this relationship, I would have that my work done is simply going to be a negative, which I will bring outside, negative integral from point A to point B of what now? KQ Q0 divided by R squared multiplied by the R. So this is what the work done will be. So the next thing we want to do is to be able to integrate it. In order to integrate this, you should understand that KQ and Q0 are constants because you're integrating with respect to R. So I'll bring this constant out and then integrate. So if I do that, I would have that my work done is going to be, I'll bring them out, minus K Q Q0 integral from point A to point B of 1 over R squared the R. So this is what I would have, right? Now, to integrate 1 over R square, what you simply do is to write that in index form. You should know that 1 over R square is same thing as R raised to power minus 2. So if I do that, I would have minus KQQ naught integral from point A to point B, R raised to power minus 2 dr. So when you integrate, when you are integrating, what do? You add 1 to the power and divide by the new power. So if I add 1 to this power, it means I would eventually get minus 1. So I will divide also by that minus 1. And my work done is going to be minus K QQ naught divided by, okay, times R raised to power minus 1 divided by minus 1. So from point A to point B. So this is what I would have. So that if I finally evaluate that, I would have that this negative would fizzle this one, right? And R to power minus 1 is 1 over R. I would have this equals KQQ naught divided by R, right? From point A to point B. So how do I evaluate this boundary? Simple. Wherever you see R, you're going to replace with RB minus. Wherever you see R, you replace with RA. So if you do that, you're going to arrive at our final relationship. KQ Q naught into 1 by RB minus 1 by RA. So this is what you would get. So the formula we have derived now is the formula for work done in moving a positive test charge from point A to point B in an electric field. And we explained that that work done is the same as what? Change in potential energy. So the work done between 2 points A and B is same as change in potential energy between the points A and B. So you take note of this as our first derived relationship. Now, change in potential energy is not exactly the same as potential energy. So potential energy is just the potential at one point, right? The potential energy at one point. While change is the difference between potential energy at one point and the potential energy at another point, right? So that is what we've gotten. The next thing we want to get is potential energy at one point. Now, if we assume in this case that the test charge is located at a very far distance, remember we started by placing the test charge at point A and trying to move it to point B, right? Now, if in this case we assume that that test charge is at a very far distance, say infinity, so we're trying to move it from infinity, a far point, to point B. So in that case, we're going to have that the work done, which is change in potential energy, UB minus UA, is equal to what now? KQQ naught into what? 1 by RB minus 1 by infinity. So remember, we're moving it from a far point, infinity, to a point in the field, which is point B. So it means that the potential energy at infinity, which is UA, is going to be 0. So if you solve this, because 1 by infinity is 0, so if you solve this, you would have that UB is equal to this 0, which is for this. So UB is equal to KQQ naught divided by RB. So for the sake of generalization, I'm just going to remove this B and simply say that electric potential energy U is equal to KQQ naught divided by R. So what is electric potential energy? It is the work done in moving a positive test charge from a point at infinity to a point in an electric field. So that is electric potential energy U. So, and I'll call this equation 2. Now, what do you need to know about electric potential energy? electric potential energy is measured in joule, and electric potential energy is a scalar quantity. It is a scalar quantity, so you take note of that. And the next thing we want to derive is the formula for electric potential, V, electric potential. And what is electric potential? Electric potential is the work done on a unit test charge. That is to say, electric potential is the work done in taking 1 coulomb of charge from a point at infinity to a point in an electric field. The work done in taking 1 coulomb, a unit, 1 coulomb of charge from a point at infinity to a point in an electric field. So I'm going to derive the formula by saying that electric potential V is equal to the work done from infinity, which is now U, divided by what now? Our test charge. So this is the formula for electric potential. Remember, electric potential is actually voltage. It's same thing as voltage. So if it is same as voltage, then what is the unit? Thank you, you are correct. The unit is what? Volt. Or, now remember this is joule. So you can say joule per what now? Per coulomb. So the unit of electric potential is volt, or what? Joule per coulomb. I believe this is very clear. Now you should also note that electric potential V is a scalar quantity. Electric potential energy is a scalar. Electric potential V is also a what? A scalar quantity. Now if you do this, remember we have a formula already for you. So I can simply say that V is equal to, from here still, is equal to U times 1 divided by Q naught. So that when I substitute, what is my U? This is my U. KQ Q naught divided by R. This is my U. Then times 1 by Q naught. So what would happen here? Q naught would fizzle Q naught. And I would finally arrive at V equals KQ divided by what now? R. So this is my third derived equation, right? Now, so notice the difference between these two. This has to do with only one charge, which is a source charge, while this one has to do with both charges. So this is the formula for electric potential energy. This is the formula for electric potential V, right? Now, the last thing I want to do as a bonus for you is to give you another relationship, an extra relationship in electric field. So that's going to be a relationship between V and electric field intensity. So if you recall, E, electric field intensity E, is given as K Q divided by R square, right? Which I can simply write as K Q divided by R times 1 over R if you separate it. So that when you say R times R, it will still give you R squared. Now, if you watch very carefully, you would observe that KQ divided by R is same as what? V. Thank you. So what can I do? I can simply say that E is equal to what? V divided by what now? R. So that you can finally say that V is equal to what? ER. Some persons may say V equals ED or V equals EL. What is our V here? Electric field intensity. So this is our bonus equation 4. Now take notes. Electric potential energy is a scalar quantity. Electric potential V is a scalar quantity. Electric field intensity is a vector quantity. So take note of these differences. I believe these concepts are very clear to you. Thanks for watching my video. Do subscribe to my channel, like and share with your friends so that they can benefit. I will be doing more videos solving problems under this now so that you can digest this very well, right? Thanks for watching. Remember, this is Prime Concept.